We are told, find all values of c such that the parabolas y equals 4x squared and x equals c plus 2y squared intersect each other at right angles, or 90 degrees. Okay, so we see that we have two parabolas here. One is 4x squared and one is x equals c plus 2y squared. So it's a good idea to see visually what it means for these two parabolas to intersect each other at right angles. Once we see them intersecting at right angles, we can think about how to solve for our c here. Okay, so let's draw our first parabola, 4x squared. So whenever we see x squared and no other x term, the vertex of our parabola, the lowest point, is always at 0, 0. So just a rough sketch of this parabola might look something like this. It doesn't really matter what our coordinates are, we're just getting a rough sketch. So this 4 doesn't really matter for us right now. So our second parabola is a little bit trickier because we don't have this y isolated by itself. It's a lot harder to draw it when it's not isolated, but we can isolate for y, and then we can draw this parabola. So let's do that. Let's isolate for y. So I can subtract c from both sides, and if I do that, I'll get that 2y squared is equal to x minus c. If I multiply both sides by 1/2 times 2 is 1, and I have 1/2 times x minus c. Now, we see that we have a y squared here, so we'll have to take the square root of both sides to get y by itself. However, notice that in our original equation, there's a y squared. So what does this mean? This means that for the same x value, you can have two different y values. What's the reason for that? Well, imagine some x value where the coordinate, the point, y equals 2 works. So this is a coordinate on our second parabola. So 2 squared would be 4, and remember c is just a constant, so x would be equal to c times 2 times 4. However, if you plugged in -2, you would get the same answer. -2 squared is 4, so x would also equal c plus 2 times 4. So you would have the same x coordinate for two different y coordinates. So what you have to realize is that you have to take the positive and the negative square root to isolate for y for this parabola. So y is equal to the positive and negative square root of 1/2 times x minus c. And I'd like to simplify this a bit. Well, I'd like to take this constant out of this square root. So let's do that. Let's say that this is equal to the positive or negative square root of 1/2. I can separate what's under the square root. So times the square root of x minus c. So this is of course plus minus 1 over the square root of 2 because I took the square root of the denominator and numerator. And I'd like to rationalize this denominator. I'd like to say that this is equal to the square root of 2 over 2. And what I did was I multiplied the numerator and the denominator by the square root of 2. So if I keep my square root of x minus c there, I get that our second parabola, we can call it y2, is equal to the plus or minus square root, the plus or minus square root of 2 over 2 times the square root of x minus c. Alright, so what is this function, y2 equals plus or minus the square root of 2 over 2 times the square root of x minus c? What does it look like on our xy plane? Well, we can see that the main component of this parabola here is really the square root of x. The square root of 2 over 2 is a vertical stretch factor. It'll stretch all our y coordinates of this parabola. And this c over here, since it's under the square root with this x, this c is the horizontal displacement. So we don't know what this c is, but our parabola here might look something like this. If c is 0, then our parabola might look something like this. So if I draw the part above the x-axis, and remember this is a plus or minus square root, so all of these y values, I also have to take their negatives, right? Because you have to take the negative square root as well. So one thing to realize about this c, as I said, is that it's the horizontal displacement of this green parabola. So depending on what this c is, our parabola might be a little further up here or a little further back. But the thing to realize is that no matter what c is, this part of our green parabola below the x-axis is not meaningful to us. Why is it not meaningful? Because this part of the green parabola below the x-axis will never intersect with our orange parabola, 4x squared, because the lowest point of y equals 4x squared is the point 0, 0. So we're looking at where these two parabolas intersect at right angles. Well, they don't intersect at all for the negative part of our y2. So for the purpose of this question, really, we can just ignore the bottom part of our green parabola. And again, that's because this c, it doesn't affect whether this bottom part of our green parabola moves up or down. It only moves our green parabola left or right. So really, we can just say that y2 is equal to the positive square root of 2 over 2 times the square root of x minus c. So we don't need the plus or minus because without it, it's implied that you're taking the positive square root of x minus c. So that's helpful to us because that makes taking the derivative a lot easier. We don't have to figure out how to take the derivative using this equation. We can just take the derivative using our new equation for y2 here. So before we get into derivatives, let's think about what intersect these two functions. Now that this is a function, let's think about what these two functions intersecting at a right angle looks like. So let me move, so this c, it can move our green function left and right, correct? So let's say our green function is somewhere over here, put something like that. Well, it won't really bend like that, but let's say something like that, and it keeps going, right? So you might be wondering, how can two curves intersect each other at a right angle? You need two lines to make an angle, right? Well, you can really just look at the tangent lines to the curves at the point at which they intersect. Why? Because the tangent line to the curve, where they intersect, each curve, is the slope of that curve at that exact point. So if you look at the slope of each curve at the point of intersection, you will get a line, right? You need a line to see the slope. And if you look at the intersection between those two tangent lines, you will get the angle at which these two functions intersect. So let me draw, this is the point of intersection. Let me draw two tangent lines. Let's say our green parabola's tangent line is something like that. And our orange parabola's, our green one isn't a parabola anymore. Our green function's tangent line is something like this, and our orange one's is something like this. So you can see they intersect at about 90 degrees. So essentially, we want to come up with an equation to find where the slopes of the tangent lines are perpendicular and where the point of intersection is. So let's write down some criteria for when two curves intersect each other perpendicularly. So two functions intersect at 90 degrees when. So one thing we know is that their tangent lines have to be perpendicular. Well, when two lines are perpendicular, their slopes, the slope of the lines, are the negative reciprocals of each other. So what does that mean? If I say the slope of this green line is m1, right? M I'm going to call it m2 because we're calling our second function here y2. Oh, and by the way, might have gone erased, but y1 is equal to 4x squared. So we know that the slope of this green line, we know that it has to be the negative reciprocal of the slope of the orange line. So you're taking the slope of the orange line, taking the reciprocal, and multiplying it by -1. That's what the negative reciprocal means. So when two lines are perpendicular, you know their slopes have to be like this. Another thing that we know is that where this happens, y1 has to be equal to y2. What this means is that the point at which they have perpendicular tangent lines is a point where the two functions have to intersect. Now that might seem kind of obvious, but I'll tell you where, I'll give you a situation where the first one might be true, but the second one is not. So just a little sketch. So let's say I had a parabola like this, and a parabola below it like this. Now, let's say I took the derivative at the same x-coordinate, because you know that when you have an equation for your derivative, you plug in your x value. So if I create the tangent line to my upper parabola here, I get something like that. Take the tangent line to my lower parabola, I get something like that. Now, do you see here that the tangent lines are indeed perpendicular to each other, but that the two parabolas themselves don't intersect each other? So that's the issue, right? We need to make sure that these two parabolas do indeed intersect each other, and of course at a right angle. So to ensure that these two functions intersect each other, we need to make sure that y1 is equal to y2. Now, one thing I'd like to mention about this second criterion is that there's likely no situation where this orange parabola and this green function have their tangent lines intersecting at 90 degrees, but the functions themselves do not intersect. That is because the situation I showed you with these two white parabolas, this lower parabola is far below this upper parabola. And that will never be the case with our orange function and our green function, because this c here, as we've mentioned, can only move our green parabola to the right or to the left. And you can think about what would happen to the tangent lines and their intersections if you moved this green function left and right. There is no situation where the tangent lines at a certain x-coordinate intersect at 90 degrees, but the functions themselves don't intersect. There's no situation like this. Why is this criterion helpful to us? Well, it's because if we use this equation and end up getting more unknowns than our number of equations, and our number of equations, if we only use our first criterion, is 1, we can use the second relationship to come up with another equation in case we have two unknown variables, and as you'll see, that'll be the case. But let's focus on this first criterion, on making this equation. To make this equation, we'll have to find our m1 and m2. Now remember that m1 is basically an expression for the tangent line to our orange parabola. For the slope of the tangent line to our orange parabola, an expression for that. Now, what's the slope of the tangent line? What's another word for that? Well, that's just the derivative. So really, to find m1, we have to take the derivative of our orange parabola, or this equation here, y1. The orange parabola is our y1, so to find m1, or an expression for it, at least, we have to take the derivative of y1. And the same thing with m2. We have to find the derivative of our function y2. And that's why it was helpful to turn our green parabola into sort of a half parabola instead of, dealing with this right here. Because then we would have had to use a technique called implicit differentiation, and that would have gotten messier. But now, all we have to do to create this equation is to take the derivative of y1, plug it in here, and then take the derivative of y2 and plug it in here. So let's do that. So number one, we are checking that I'll use this color. Our m2, the derivative of y2, is equal to negative 1 over m1. Alright, so between y1 and y2, y1 looks easier to take the derivative of, so let's start with that one. So we are going to say that d over dx of y1 is equal to d over dx of 4x squared. So I'm taking the derivative of both sides of this equation. And that'll keep the equation the same, of course. Okay, so if I take the derivative with respect to x of y1, that just becomes dy1 over dx, and really, this is the derivative of y1, and really that's equal to m1. Now the thing we have to use our derivative rules for is 4x squared. So of course you can take this 4 out of the derivative brackets and then just multiply by d over dx of x squared. Now you might remember that the derivative of x squared is 2x, but in case you need a reminder of the power rule, I'll do an aside here. D over dx of x to the n is equal to n times x to the n minus 1. We subtract 1 from our exponent and put our original exponent out of the front. So the derivative of x squared is of course 2x. So that means we have 4 times 2x, and of course 4 times 2 is 8. So this is equal to, I'll do it in our darker orange because that is color we're using for m1. That is equal to 8x. So that means m1 is equal to 8x. Now the thing that's a little harder to take the derivative of, just because there's a square root, and x minus c is y2. But let's do it step by step. So we are finding m2, and to do that, we're going to take this equation we have here and take the derivative of both sides. So d over dx of y2 is what we're doing. And really, there's nothing to do with this y2, we're just doing this so you can see that I'm taking the derivative of both sides and therefore keeping the equation the same. Alright, when we're taking the derivative of an expression where there's a constant out front, we can always take that constant out and just take the derivative of whatever x is in. So that's square root of 2 over 2 times d over dx of the square root of x minus, where's our pink? X minus c. Alright, so you might see here that this is a little more complicated than if we just had square root of x. If we had the square root of x, we could use our power rule, but there's a little bit of chain rule going on here. And I wonder if you can see it. And the reason there's chain rule is because our outer function here Just a reminder of what chain rule is first, actually. Chain rule is when you're taking the derivative of a composite function. A composite function is when you have a function f, and inside that you have another function, g of x. So the derivative of f of g of x, well, the rule says that this is equal to f prime with respect to g of x multiplied by, so this is the derivative of derivative of f with respect to g of x. That means if you took the derivative of f of x, in that expression wherever x is, you plug in g of x, and you multiply that by the derivative of g of x, g prime of x. So what we have to do here is we have to identify what is f of x and what is g of x. We have to figure out what's the outer function and which function is inside that, and then we can use this rule here. So and each of these has to be something we know how to take the derivative of. So what I'm recognizing here as our outer function, something we know how to take the derivative of, is the square root of x. F of x should be the square root of x, and therefore our g of x should be x minus c. So if we say that f of x is equal to the square root of x, that is something we know how to take the derivative of, and we say that g of x is equal to x minus c, we also know how to take the derivative of this. Well, of course, f of g of x is equal to, we'll do it in our original green here, the square root, actually I'll do this, the square root of x minus c. And then we would apply this rule. So let's do that, apply this rule. To find f prime with respect to g of x, we're going to find f prime of x and then just plug in g of x. That's what makes it f prime with respect to g of x. Wherever there's x in f prime, you plug in g. If f prime is f of x, then, if f of x is the square root of x, then f prime of x must be the derivative of this. And how do we find the derivative of the square root of x? Well, the square root of x is really x to the power of 1/2. That's what taking the square root of something is. You're taking something to the power of 1/2. So, since we have x to the power of something, our n, we can use the power rule. So this is equal to, our n here is 1/2, so we're gonna bring this n to the front. So we have 1/2, and we're gonna multiply it by x to the power of 1/2 minus 1. So what's 1/2 minus 1? Well, 1 is really 2/2, so we can have the same denominator. And 1/2 minus 2/2 is negative 1/2. So this is x to the power of negative 1/2. And when you take something to a negative power, you bring it to the denominator. You make 1 over that x to the n, and you make the exponent positive. So this is equal to 1/2 times 1 over, I'll make this red actually so you can understand the next step, x to the 1/2. And if we multiply this out, 1/2 times this, we get 1 over 2 times the square root of x. Now, to make this f prime of g of x, we have to plug in g of x, where x is. That makes it f prime of g of x, not just f prime of x. So what does that mean? That means that f prime of g of x is, of course, equal to 1 over 2 times the square root of, not x, but x minus c, which is our g of x. All right, now we have half of this rule, f prime of g of x, right there, but we have to multiply it by the derivative of g of x. Now that's pretty easy, because all we have here is x minus c. Now you might remember that c is a constant. The derivative of a constant is 0, so we really just take the derivative of x. And this is 1 times x right here. And the derivative of x, you can think about it with the power rule as well, but the derivative of x is just 1. So that means that g prime of x is equal to 1. This means that m2, as we've said, is the derivative of, the square root of 2 over 2 times the derivative of the square root of x minus c. And this is equal to this times this, because that's what our chain rule says. And multiplying by 1 keeps an expression the same. So, of course, this is equal to 1 over 2 times the square root of x minus c. Alright, so I realized that one mistake that I made with my m2 here is that I forgot to multiply back the constant. It's alright, we all make mistakes sometimes, but let's make sure we do that. So if you remember, this is the derivative of just our square root of x minus c. But we have to remember to multiply back our, let's move this over a bit, or I could just write it here. We have to remember to multiply back our square root of 2 over 2. This is the same constant that was here. So I took the derivative of square root of x minus c, left this constant separate, but we have to remember to multiply it back. And we can just do the multiplication here. So our numerator will be 1 times the square root of 2. That is equal to the square root of 2, of course. And in our denominator, we have 2 times square root of x minus c times 2. So that 2 times 2 will become 4, and we'll be left with, I meant to write 4. 4 times the square root of x minus c. Alright, now we really have our m1 and m2. Okay, so our next step, which comes from our first criterion, by the way, is to plug in our m2 and our m1. And remember, this is the equation that makes sure that the tangent lines of our two functions intersect at 90 degrees. When two slopes are perpendicular, they'll be equal to the negative reciprocals of each other. So if we bring our m2 to the left side, we get the square root of 2 over 4 times the square root of x minus c is equal to negative 1 over m1. And our m1 is 8x. Now, remember our original goal, what the question is asking us, is to find c. Now, what we need for that is one equation that has only has c as the only unknown variable. And this equation right here, we have x and c as unknown variables. That is a bit of an issue, but that is exactly where this second point is useful to us. And we will get to the second point. But what would be a useful thing to do with this first equation is to isolate for c, because c is the variable we're trying to find. So it's easier to work with it if we isolate for c. So how do we do that? Well, we can start with cross multiplying. So let me move this over a bit. So to cross multiply with this, we are going to multiply both sides by 4 times the square root of x minus c. So 4 times the square root of x minus c, and multiply both sides by 8x. So that'll get rid of our fractions here. It's easier to work with things when they're not in fractions. So this 4 times x minus c will cancel out with this one to make 1, and this 8x will cancel out with this 8x. So we will be left with, on our left side, let's make it blue, pretty neutral color. We will be left with the square root of 2 times 8x, and that is equal to negative 1 times 4 times the square root of x minus c. Well, that is equal to negative 4 times the square root of x minus c. Now remember, we're isolating for c here, and that means we have to take this square root, we have to get rid of the square root here. To get rid of a square root, you have to square both sides. So let's do that. Let's take each side as a whole thing and square. So if we square our left side here, notice square root of 2 is multiplied by 8x, so we take square root of 2 squared and 8x squared. So if we square the square root of 2, we get, of course, 2, and 8 squared is 64, and x squared is, of course, x squared. Now, same thing on this side. So negative 4 squared, it doesn't matter that it's negative, it's still positive 16. And that's multiplied by the square root of x minus c squared. Well, of course, that's just x minus c. Now, we have some very nice numbers to work with here. We can divide both sides by 16. So if we divide this side by 16, we get 16 over 16, which is 1. And if we divide our left side by 16, 64 divided by 16 is 4. So on our left side, we get 2 times 4 times x squared, and on our right side, we just get x minus c. And this 2 times 4 here is, of course, 8. Okay, if we do a little bit of rearranging and bring c to our left side and our 8x squared to our right side, we can say that c is equal to negative 8x squared plus x. Now, we do have only one equation and 2 unknowns. That is a bit of an issue, but remember, we have our second criterion. And it says that y1 must be equal to y2 where the two functions intersect at 90 degrees. So let's make this equation. We have an equation for y1 and we have y2. So let's set them equal to each other. And you might notice we'll get another variable with x in it, another equation, sorry, with x in it and c in it. Okay. So let's do it on the right over here. So second criterion, checking that. Y1 is equal to y2. Now, no derivatives from this part are now on, just algebra. So first step is to plug in y1, and y1 is 4x squared. So 4x squared is equal to y2. y2 is this thing. So on our right side, we have square root of 2 over 2 times the square root of x minus c. Now, let's do the same thing. Let's isolate for our c to make things easier. So the first thing we can do is multiply both sides by 2. I would say that's the easiest thing that we can do right now. Let's make it blue again. So if we multiply both sides by 2, we get this 2 and this 2 canceling out, and 2 times 4 is, of course, 8. So we get, let me zoom in a bit so you're not seeing the other side. We get 8x squared. And on the right, we have the square root of 2 times the square root of x minus c. So again, we have to get this c out of the square root first. So a good way to do that right now is to square both sides. So if we square both sides, on our right side here, we have to do 8 squared and x squared squared. So 8 squared is 64, and x squared, take that to the power of 2. You have to multiply the exponents, and if you multiply the exponents, you get x to the 4. And we are doing the same thing on the right side. So the square root of 2 squared is 2, and the square root of x minus c squared is, of course, x minus c. Now, let's divide both sides by 2. So 64 divided by 2, 64 divided by 2 is 32 times x4, and that's equal to x minus c. All right, let's do the same thing we did with our first criterion. Let's isolate for c. So bring the c to the other side, and bring the 32x to the 4 to the other side. You get that c is equal to negative 32 times x to the 4 plus x. All right, now this helps us a lot. Oh, why? Because now we have two equations with the same two unknowns. We have one equation with x and c and another equation with x and c. And notice our work is pretty simple now. We know that c must be equal to this expression with x, and it also must be equal to this expression with x. So we can really just set these two equations equal to each other. Now let me go through with that. So let's call this section 3, solving for x, and then once we find some values for x, we can just plug it into one of these equations. And once we plug it into this equation, let's say, we will get an actual number for c, and that's exactly what we're looking for. Real values for c. Alright, so we're going to set these two equations equal to each other. C is of course equal to c, and that means that negative 32x to the 4 plus x must be equal to negative x squared plus x. Now I see a plus x on both sides. We can just get rid of that. Simplify it a little. Okay, now I have two x terms here, and they're of different powers. And the easiest way to solve for x when you're doing this is to bring all your x terms to one side and make the other side 0. That way we can factor it and see what values of x work. So we'll get negative 32x to the 4, and if we add 8x squared to both sides, we get this. We have made one side 0, and the other side this expression. So, to find values of x that make this equation true, we have to factor our expression with x here. So let's do that. Let's take an x squared out of each term. So if I do that, I get x squared. Actually, let's take an 8x squared out of each term, because each term here is divisible by 8x squared. Or negative 8x squared is actually even easier. So I hope I'm not going too fast, but if I take negative 8x squared out of this term, I'm essentially dividing by negative 8 and x squared. So I'll put my negative 8x squared out here. I will get positive 4 times x squared. Notice if you multiply it back, negative 8 times 4 is negative 32. X squared times x squared is x to the 4. Now here, if I divide this term by negative 8x squared, I just get negative 1. And it works if you multiply it back. And of course that's equal to 0. All right, how do I factor this even further? Well, one thing I see here is a difference of squares. Now, a reminder what difference of squares is. That's when you have a number squared or a term squared minus another term squared. You know that this is equal to a minus b times a plus b. And that's what I see here. Our a squared, looks to be 4x squared, and our b looks like 1. See, 4x squared minus 1, a squared minus b squared. So that means our a must be the square root of this, and the square root of 4x squared is 2x, and the square root of b squared, and the square root of 1 is of course 1. So if I want to make 4x squared minus 1, which is a squared minus b squared, into a minus b times a plus b, I'm going to do this. I'm going to keep my 8x squared out front here. A minus b, so a is 2x, b is 1, so 2x minus 1, and our a plus b is 2x plus 1. And all of that is equal to 0. Okay, there is no way I can factor this further, but that's alright, because now we can find what values of x make our equation true. So one value I see, and let's make this red. One value I see that works is 0, because if you plug in 0 for x, you'll have 8 times 0, which is 0, and 0 times anything is just 0. That makes our equation true. 0 is of course equal to 0, so that means x minus 0 must be a solution to this equation. Our x can take on the value 0 when we're setting these two equations equal to each other. Let's check our next bracket here. We're checking all the factors. So looking at this bracketed expression here, we know that 2x minus 1 must be equal to 0 for this equation to be true, because 0 times anything is 0. If we isolate for x, we get x is equal to 1/2. I brought 1 to each side and divided both sides by 2. Now, what about 2x plus 1 is equal to 0, making this factor 0 so that the equation is true? We get that x is equal to negative 1/2. If you subtract 1 from both sides and divide by 2, you get that x is equal to negative 1/2. Now look at that. We have 3 values for our x, and we have an equation to plug x into to get our values for c. And by the way, it's okay that we got multiple values for x, because our question asks what values of c work. Values plural. So let's do that now. Now our job is to just quote do the math. We have values of x that x can take on when these equations are true, and we can just plug it in to get our value for c. So let's do that. So number 3, continued, finding c. So c is equal to, let's do case 1, where x is equal to 0. So this is x is equal to 0. We have negative 8 times 0 squared plus 0. Now, of course, this is negative 8 times 0 plus 0, and that is equal to 0. So 0 is a value that c can take on. And that makes sense, because think about this function where c is 0. It's the square root of x times a constant. And that will bring our green function right here. So where the orange parabola intersects with the green function has a vertical tangent line, and the orange parabola has a horizontal tangent line, and of course they intersect at 90 degrees, if that's true. Now for our next case, where x is equal to 1/2, we get that c is equal to negative 8 times 1/2 squared plus 1/2, and that 1/2 squared is 1 over 4. So we get negative 8 times 1 over 4 plus 1/2, and negative 8 times 1 over 4 is negative 2. But if I want these two terms to have the same numerator, I can say that negative 2 is negative 4 over 2. So negative 4 over 2 plus 1 over 2. And that is equal to negative 3 over 2. And now for our final case, where x is equal to negative 1/2. So this means that c is equal to negative 8 times negative 1/2 squared, and we're adding negative 1/2, which is really subtracting 1/2. So this, I'll bring it a bit lower. So this is equal to negative 8 times 1 over 4, because even though it's negative, if you square it, it still becomes positive 1 over 4. We are subtracting negative 1 over 2. So this becomes negative 8 divided by 4 is negative 2, minus 1/2. We get negative 2 is really negative 4 over 2 minus 1/2. And this is negative 5 over 2. And that is our final answer. So therefore, this is our big therefore statement. C can be equal to 0, negative 3 over 2, or negative 5 over 2. All right, I hope that helped.